Hey everyone, Mr. Andrew here. Today I just wanted to create a short video going over how do we create proper Lewis dot structures for covalent compounds. So previously, we've done this with ionic compounds where we diagram out how electrons are being donated or transferred from one atom to another. But with covalent compounds, it's a little bit trickier because there are multiple kinds of covalent bonds. So how do we know what kinds of bonds to use? How do we know what these atoms look like? Well, there are some ways that we can diagram these out using Lewis dot structures. So let's look at some of these today. So let's start out with a relatively simple one, right? Let's start out with something like, start out with CH4. Okay. So CH4 is a covalently bonded compound. We can tell because they're all nonmetals here. Remember, hydrogen is not a metal, it's an exception. Okay. Even though it's a group 1, it is not technically a metal, it is a nonmetal. So, how do we figure out what this looks like? Well, there's actually a process to this. Okay. So, first, we have to calculate the number of bonds. Okay. We need to figure out how many covalent bonds do we need. Okay. And there's actually a pretty straightforward way of doing this. Okay. What we do is we need to figure out, first of all, how many electrons do we have in total? Okay. So carbon is right here on the periodic table. So we know that it has 4 valence electrons. Okay. Hydrogen is a group 1 element. It's right here. So hydrogen has 1 valence electron. But there are 4 of them. So we have to multiply this by 4. So that means in total, hydrogen has 4 electrons. Okay. So with all of the atoms together in this molecule, we have 8 electrons available. Okay. Next, we need to figure out how many electrons are required to meet the octet rule for all of these together. Okay. And it's really simple because basically every atom wants 8 with a couple of exceptions. Okay. And really, those exceptions are just hydrogen. That's basically the only exception you're going to find. You could also say helium because these are both in period 1, but helium's not really going to react. So that never comes up. So these are the electrons available. We want to see how many we need. So carbon, it wants 8 electrons. Hydrogen wants 2 electrons because, again, it's only in period 1. But again, there's 4 of these. Okay. And you know what? To clean this up and make it look nice, multiply those by 1 so you guys can kind of see that clearly. Okay, so 8 electrons times 1 means carbon needs 8 electrons. Each hydrogen wants 2 electrons, and there's 4 of them. That's another 8 electrons. So in total, if each of these met the octet rule on their own, we would need 16 electrons. Now, here's what's critical. Each electron in a covalent bond gets counted twice because both atoms on either side of that bond actually do see that. They actually do get they get credit for that, basically. So basically, the difference between these two is going to help us figure out how many covalent bonds do we need. So what we do is we take the number of electrons that we need and we subtract the number of electrons that we have. Okay? And the result is that we're 8 electrons short. Okay? So if we were to just fill these up with the electrons we've got, we would be 8 electrons short. But for each covalent bond that we have, we get credit for 2 electrons. So as a result, we have to take the number of electrons we're short and divide it by 2. So 8 electrons divided by 2 means we need 4 bonds. We need 4 covalent bonds. Now, when I say 4 bonds right here, what you should know is that a single bond it counts for 1, a double bond counts for 2, and a triple bond counts for 3. Okay? So this 4 bonds could be 4 single bonds, because that would be, 4 ones. It could be a double bond and 2 single bonds, because that would also be 4. It could be a triple bond and a single bond, that would be 4. Or it could be 2 double bonds, 2 and 2, that would be 4. So, how do we figure this out? What do we do? We did get a new piece of information, but how can we draw this out? So, here's what we do. There are some rules as far as how these atoms have to be arranged. The biggest rule is the atom with the lowest electronegativity is in the middle. Okay? The atom that has the lowest electronegativity is the central atom. So remember, calling back to Unit 3, okay, electronegativity increases as you go up and to the right on the periodic table. This means that the more an atom is to the lower left, the lower the electronegativity, and therefore the more likely it is to be in the center. But there's an exception to this. Hydrogen can never be in the center. Hydrogen can never be in the center, and I'll show you why in just a little bit. So, because hydrogen can't be in the middle, the only other atom in our molecule, which is CH4, remember it's up here, is carbon. So carbon's got to be in the middle. Okay? So now I'm going to arrange the hydrogens around it, 1 on each side. Okay? 1, 2, 3, 4. And I'm going to connect all of these by single bonds. 1, 2, 3, 4. And luckily for us, the only way that we can connect these all together is we need 4 bonds. And because we only have 4 bonds, that means that we're done. We've met the octet rule. And if we look at our Lewis dot structure, we can actually see that. Remember, hydrogen only wants 2 electrons. So this bond right here counts for hydrogen. That gives it 2. Remember, each bond is 2 electrons. And that is the same for all of these. Okay, all of these hydrogens have 2 electrons next to them, so they all meet their octet rule. Okay. Carbon, on the other hand, right here, has all of these electrons around it. So 2, 4, 6, 8. That's 8 electrons right there. So carbon has also met the octet rule. And as a result, all the atoms are happy. They all become more stable as a result. Okay. Let's try another one. Let's try one that's a little bit more challenging. I'm just going to get rid of all this stuff right here. Right there. Let's pick one that's a little bit more challenging. Let's do CO2. Okay, CO2 is carbon dioxide. So we want to see what this molecule looks like. So we're going to start with the first rule. Okay, first rule was calculate the number of bonds. So how many bonds does carbon dioxide have? So carbon dioxide, you have carbon and oxygen. Carbon has 4 electrons, and there's 1 of them, so we're going to get 4 electrons out of the carbons. Oxygen, there's 6 electrons, and there's 2 of them, so we're going to get 12 electrons out of this. Now, if we add these together, we have 16 electrons available. Okay. Now, we want to calculate how many we need. Now, the good news is, basically, this calculation is pretty simple because everything wants 8 except for hydrogen. So you really can think about it as either hydrogen or not hydrogen. We don't have any hydrogens here, so means all atoms, they want 8 electrons, and there's 1 carbon, 2 oxygens, so there's 3 atoms in total. It means we need 24 electrons. Okay. Now, we want to calculate how many are we short. So 24 electrons needed minus 16 electrons that's available. That means we're short 8 electrons. Divide that by 2. Means we need 4 bonds. Okay. So we're 4 bonds short. How are we going to make this molecule? So we're going to follow the rules. So the second rule is lowest electronegativity is in the middle. Because electronegativity goes lower as you go down and to the left, and carbon is in the same row, but to the left of oxygen, it means carbon must have a lower electronegativity. So carbon has to be our central atom. And I'm going to put the oxygens on either side. Okay. Now I'm going to connect these by single bonds. Okay. I've used up 2 of my bonds. Okay. Now, here's what we have to understand. Each bond is 2 electrons, and we need 4 bonds. So that means 8 electrons are going to be in bonds. And if we take that away from the total we have available, it means 8 electrons are not in bonds. Okay, so we have 8 electrons that are not in bonds. So we need to put them somewhere on our model. We know that there's going to be 2 more bonds that are added in these spots. Okay, and actually it kind of makes sense to just put them in there right now, because we can see that it would be easy. That is not a very straight line. To put the bonds right there. Sorry, it's going to bother me. Okay. So now we've used up 4 of our bonds. Okay, so we have used up all of these. As a result, carbon right here has 4 electrons on the right and 4 electrons on the left. It has met the octet rule, so it does not want any more electrons. But we still have 8 electrons that are not in bonds that need to be used. We can't just get rid of these electrons, right? So we need to put those electrons on the 2 oxygen atoms. Okay, so now we have 2, 4, 6, 8 electrons that are not in bonds. These electrons that are paired up but they're not used in bonds, these are called non-bonding electron pairs, and we'll talk about them a little bit more later. But as a result of these, this oxygen now has 8 electrons around it, 4 of them from the bonds and 4 not in bonds. And the same thing can be said about this one. So, as a result, let's just go back. That's better. As a result, this whole molecule now meets the octet rule. Each atom has 8 electrons. So, it's happy. So, we can see that we can do this process for basically any atom, or I'm sorry, for any molecule. Okay? Let's try one more. Let's do one last problem. And this time, let's do one where the bonds are kind of mixed up a little bit. Okay? Let me show you what I mean. Let's do C2H4. Okay? C2H4. This is another covalent bond. Okay? Let's figure out how many electrons we need. Or, I'm sorry, how many we have first. So, carbon has 4 electrons, and we have 2 of them, so it's going to be 8 electrons available. Hydrogen, 1 electron each, and there's 4 of them, so that's 4 electrons available. So in total, we have 12 electrons. Okay. Now, how many do we need? Carbon wants 8 electrons, and there's 2 of them, so it wants 16 electrons. Hydrogen, each one wants 2 electrons, and there's 4 of them, so that's 8 electrons. We add these together, and we have 24 electrons needed. Okay, do our quick calculation. 24 electrons needed minus 12 electrons available equals 12 electrons short. Divide that by 2, and we need 6 bonds. Okay. Now, again, we can take a quick look right here and see we have 12 electrons available. We need 6 bonds. These 6 bonds are going to take 12 electrons to make. So there are going to be no unpaired, or not unpaired, non-bonding electrons. Okay. So we're going to try and draw our molecule. And it says right here, lowest electronegativity goes in the middle. But it can't be hydrogen. Now, why can't it be hydrogen? It's because if hydrogen was in the middle, right? By definition, when you're in the middle, there's going to be something on either side of you, right? And so hydrogen would have to have a bond on either side for it to be in the middle. But the problem is, each of these bonds counts for 2 electrons, which means that in total, for it to be in the middle, hydrogen would have to be surrounded by 4 electrons. This would violate the octet rule. So because of that, hydrogen is never in the center of an atom. Okay? So in our molecule, we know that carbon has to be in the center. And there's 2 carbons, so they have to be bonded to each other. Okay? Now what we're going to do is we're going to start connecting hydrogens to this. Okay? We're going to kind of keep it symmetrical. We're going to put hydrogens 2 on one side and 2 on the other. So now we've got all of our atoms, right? There's 2 carbons and there's 4 hydrogens. This matches our formula. And they're all connected by single bonds. So we've used 1, 2, 3, 4, 5 bonds. Okay? We need 6 bonds. But critically, hydrogen can't be connected by a double bond because if it was, then it would have 4 electrons. That would break the octet rule. So hydrogen can't have a double bond next to it, which means this bond, this bond, this bond, and this bond all cannot be double bonds because they're connected to hydrogens. So the only choice available to us is to have the double bond be in the middle. Now, if we check this hydrogen has 2 electrons. It's happy. And we can say that about all the hydrogens. Okay? They all meet the octet because they all have 2 electrons around them. Okay? If we look at the carbons, this carbon has 2, 4, 6, 8 electrons. It meets the octet rule. And this carbon right there also has 2, 4, 6, 8 electrons. So it also meets the octet rule. So as a result of this, each of the atoms in this molecule are happy. They're all more stable. They all meet the octet rule. And this is the Lewis dot structure for our atom. So hopefully this video was helpful in kind of giving you the foundations to start trying these on your own. Please keep practicing this skill because this does take some practice. If you have any questions, come see me anytime. I'd be happy to go over some more of these problems together with you, and I will see you next time.